Yeah. So good morning, everyone. Let's do a quick recap of the concepts that we learned the second day. So can you recap some of the concepts?
Introduction to the deep learning model and
Yeah. Intro to deep learning, of course, we did it, on the first day. Yes.
multi-layer perception.
Yeah. Pardon?
Multi-layer perception.
Yeah, multi-layer perceptron. Yeah, it's perceptron, yeah.
And the loss function for the neural networks,
Yeah, looked at loss functions.
which are feed forward and back propagation.
Okay. Let's keep it.
And optimization of the values like optimizers, gradient descent.
Yeah, feed forward and back propagation.
Yeah. Optimization of the values like
Okay.
optimizers, which is gradient descent.
Optimizer.
Gradient descent. And two parts in the neuron like summation and transformation or activation.
Yeah. Perceptron are the two core functions.
Yeah, one is summation and activation function. In activation, three methods like sigmoid, tenth, and ReLU.
Manage. Okay.
And then callback methods, I believe.
Yeah, we looked at callback methods as well.
Yes, early stopping and model checkpoint. One more I forgot.
Yeah. So reduce LR,
Yeah, reduce alarm. Yeah.
right?
Or plateau. On
And
plateau.
yeah,
Reduce alarm on plateau. Yeah.
dynamically adjusting the learning rate. We also understood what is the difference between epoch and batch size, right?
Yes. And also we looked at NLP, natural language processing.
That's the second day we looked at.
Yeah.
Yeah. Yes.
TF, IDF representation.
Okay. So the first thing that I think we looked at in NLP is primarily because NLP is a structured data, how that actually gets vectorized, isn't it?
Yep, correct.
How do I actually represent in terms of vectorization? Yeah, this is the most important part in machine learning or deep learning is how do I sometimes we also call it a interesting term called numericalize, because everything ultimately has to be converted into somewhat numbers.
Correct. The three methods we discussed: binary and town frequency and TF, IDF.
Yeah, term frequency and TF-IDF.
Yeah.
And some of the terms in NLP that you should be familiar with are like
Sample,
yeah,
corpus,
yeah. What every sample is called?
sentence.
It's called a document,
Document, correct.
right? Because it can contain a sentence, a
Or
paragraph,
paragraph. Yeah.
and the corpus. I mean, the collection of documents are basically called your what?
NLP corpus.
Corpus. The data set typically is a called corpus, right? And then
Unigram representation of the vector, each word feature.
there's a concept called tokenization. How do I actually tokenize the corpus?
Unigram
Gram or
representation vector.
right?
Dictionary.
Then we create something called dictionary.
Yeah.
Right? Dictionary is nothing but collection of all unique set of n-grams. Okay.
Unique words.
It also contain unigram, bigram, whatever. Depends on how we. Okay. And then we also understood, of course, the most widely used approach to represent NLP in terms of vectors is TF-IDF traditionally. And TF-IDF representation.
Limitations.
Hmm?
Limitations for TF-IDF.
There are certain limitations of that, right? And if your sentences are very small, typically, and corpus is not very large, still, I think your traditional TF-IDF methods give you very good results, actually. Normally, one of the most widely used algorithm we use once we represent data in TF-IDF, right? Once you represent your NLP text in terms of TF-IDF, like your X1, X2, and all that, one of the most widely used algorithm is called a naive-Bayes. Okay? Yeah, so naive-Bayes classifiers are actually very popular in terms of NLP classifications traditionally. So naive-Bayes works on the concept of, I'll just give a couple of minutes just to explain the idea here, which is pretty good, pretty much carried forward in the, even in deep learning also. The idea is that now let's say there are few sentences are there, right? Let's say there's a positive sentence which contains a word called awesome, right? And there is a negative sentence which contains a word called terrible, right? So now what we do is we compute something called what is the probability, right? The word appears awesome given that it's a positive sentence, right? This is from the training corpus, the training data, we calculate this. So we look at, how many positive sentences are there. Okay, this conditional probability can be calculated, right, based on the intersection of how many sentences contains awesome, right, intersection of positive sentences. So out of, let's say there are about 100 positive sentences are there, right? In the whole corpus, there are 200 sentences are there. Out of 100 sentences are there positive, and out of, let's say, 20 sentences contain the word awesome, right? So the probability will be 20 divided by 100, right? 0.2. Similarly, we calculate the probability. So we also calculate what is the probability that the sentence will contain awesome, given that it's a negative sentiment also, which I'm assuming that this will be, the probability will be very low. This probability will be very high. Similarly, so when we vectorize, right, we calculate this probabilities, right, across all the unigrams and from the training corpus, and we keep it, right? And then now let's say we get a new sentence, right? New sentence, and we were trying to predict, because in the training corpus we already know it's a positive, negative, and from that we calculate what is the probability that will contain these words. But in the new sentence, we have the information what word it contains, and we want to predict whether it's a positive or negative, right? There we want to calculate what is the probability that this sentence is positive, given that it contains the word called what? Awesome. Right? So you can see this is a Bayes theorem, which is nothing but PA by B. You can calculate if you know PB by A multiplied by PA, right? And of course, we calculate across multiple different words and multiply them. So this will be a dot, just a product of all probabilities across all the words that's in the sentences. Okay, so this is a very powerful algorithm, of course, and very simple algorithm that can be applied for binomial classification or even multi-class classifications also. You can calculate across. So you calculate what is the probability a word is there in the sentence, given that it's a positive or negative. And if you know this prior, this is called prior probability, right? Then of course you can calculate posterior, saying that, okay, now if this word is there in the word, in the sentence, what is the probability that it is positive, right? Similarly, if a sentence contains right? If a sentence contains the words W1, W2, W3, W4, we do a dot product, right? A dot product of all PI, right? That is a positive given there is a word Wi. I equal to 1 to n. What about the number of words we have? So this is the problem that we calculate. So TF-IDF, the whole idea basically saying that TF-IDF is basically one of the very powerful way of representing sentences. And traditionally, people have been using, of course, many classification algorithms like logistic regression, SVM, right, random forest and all that. But naive-Bayes typically was very popular model that was used to classify sentences. Okay. Okay. Any questions on this? So now coming back to the limitations of TF-IDF. What are some of the limitations of TF-IDF?
Sparse vector.
Yeah. I think one of the most important limitation is sparse vector, right? Which of course we'll discuss today. This is how it is actually taken care. Sparse vector is what? Especially there are too many zero values, right? Non-zero values are very less. It's a very wide representation. Wide means high dimensional representation of data. Okay, because the whole dictionary has to be represented as features. And remember, we took this example of IMDb classification where there are 88,000 unique words. Now imagine that we have to represent all of them as a vector space, right? And no sentence would contain more than 20, 30, or maybe maximum 50 unique words. And rest all will be zero. So that's basically sparse vector representation. Yeah, that's one limitation. Second one is what?
Difficulty in handling the synonyms and polynonyms.
Yeah. Polysemy, we call it. So what is, we don't capture the semantics of the words, right? Semantics are very important. What we capture is basically whether the word exists. We are mostly focusing on the frequency or occurrences, right? We don't actually bring the semantics, what actually the word really mean into the right. So that's one of the limitations. Third one is what?
Due to the high data, large data, it is a little bit expensive.
Context is lost.
Context is lost, right? Because we don't care about word order, right? We, irrespective of in which order the word exists, we simply represent basically it does exist or does not exist, right? And the word order itself is not taken care of, okay? And like you're saying also, we don't take care of, right, polysemy or synonym words, right? Polysemy and synonyms. So that's why there was this idea that was proposed by Google, okay, sometime back in 2016-17. I think this is probably one of the most important idea in the field of AI, okay, called embeddings. I'll come to some of the examples if you're interested, how embeddings is captured even in non-NLP world also, all right, non-NLP worlds also. So embeddings are what? Embeddings are representing entities or words in terms of numbers, which also captures their what? Semantics, right? Their meaning. For example, if we saw an example of what? Like a men, woman, king and queen, right? So if you represent them in terms of embeddings, right, in terms of some numbers, how do we generate these numbers? We'll come to, we saw one example that day, and we'll also look at some more advanced examples today. So in a way, if you can capture them into some kind of dimensions, right? Let's say D1, D2 to dk. Now, there'll be, of course, some numbers should be there. And this is basically a dense vector, right? This is not a sparse vector. This is typically a dense vector. We can compress that information into a very small number of vector space dimensions, like a 8 or a 16 or 32 or even 50, 60, whatever, right? Not necessarily it has to be always 2 to the power something. Now, if you represent them by whatever mechanism we have, and if you believe that these embeddings actually truly represent the semantics of these words, then I should be able to understand the relations between these words, the relationship between these words through simple mathematical equations or algebraic operations. For example, I should be able to do something like king minus men equal to or approximately equal to, right, queen minus woman, right? So this is what is actually written in the paper, that the embeddings they generated actually does hold this relationship, right? Or, for example, France minus Paris, right? They're basically nothing but the words, simple words, equal to India, right, minus Delhi or New Delhi, whatever it is. So these relationships are actually hold true, okay, which itself means that you know, these embeddings are truly capturing the semantics of this words. Okay. Understood? What else?
Truncation.
Yeah. So then we started looking at how to generate this, how to generate these embeddings, right? Isn't it? So to generate these embeddings, what you do is we can, because these embeddings are not given, we have to learn these embeddings from the corpus itself. We have to understand the meaning of the words from the data set itself. So what we'll do is we'll actually train a deep learning model, right? We'll train a deep learning model, which is nothing but it contains, the input layer, the hidden layer, and the output layer, right? Which is nothing but your typically, it's called a fully connected layer. Now, what we do is rather than feeding the words, right, we are going to introduce a new layer here now. Okay. This layer is called nothing but your what? What is this layer called?
Embedding layer.
Embedding layer. Right. And this embedding layer, you can imagine like, right, I'll just keep it far away. So I'm going to introduce this embedding layer here. Now this embedding layer will contain the embeddings for all possible words in the dictionary, at least in the corpus, right? So let's say I have, for the timing example, let's say I have 100 words, W1 to W100, right? And these are the different embeddings. Let's say in the dimension of 8, these dimensions actually contain the semantics of this particular word. And then when I train, initially can randomly initialize, of course. Now when I train, so I'll take a document, right, which is nothing but a sentence or a paragraph. Let's say this particular document contains the words W2, W7, W1, W9, and W40, right? So let's say these are the contains 5 different words in that order, right? Then what I'll do, I'll take W2, what are the embeddings, right? I'll take those embeddings and I'll take the embeddings of the W7, right? W2, W7, and so on and so forth until I take all the words like W40. Right? And then what I'll do is I'll concatenate them. For example, each one contains 8 dimensions. Now there are 5 words are there, so there will be 40 different values would be there, right? So now that becomes my input to my neural network. The typical, the fully connected layer, right? So that goes through then your hidden layer, multiple hidden layers in output layer, and my Y value gets estimated. Now, one challenge here is, now every sentence will not have an equal number of tokens or equal number of words, right? Some will have 5, some will have 6, some will have 100, and so on and so forth. And we know that typical neural networks, the input layer, that the input is typically fixed, isn't it? So what we need to do is that then it comes the concept of what?
Tokenization.
Uh,
Truncation.
Yeah, truncation
and padding.
or padding, right? So what I'll do is I will find out a length. What is the maximum length of the sentence that I can take, which we estimated from the distribution. Remember, we looked at the length of all possible sentences in the all possible documents in the corpus, and then we took like 95% confidence interval, and then we told, okay, what about that 552 or something, right? So that is the maximum length. Okay, so 552 maximum multiplied by 8 dimensions, right? So that becomes my input to my fully connected layer. Now, some sentence will be lesser than this, and some sentence will be larger than this, longer than this particular length. So what I'll do is I'll take care of padding if it's shorter than that, and I'll take care of take out the longer sentence to the truncation. So that way I'll feed them. And then what happens is these embeddings are not known to us at the beginning. So I'll randomly initialize them. So anything that you don't know in the model, this iterative approach, so you randomly initialize them. And then whichever task that you're doing, for example, in our case, we are doing a sentiment classification, right? We are doing a sentiment classification. So what I'll do is I will calculate the loss function here, right? And then I'll do a back propagation through which I will adjust these weights, of course, and I'll also adjust the embedding values, right? So each value I'm going to calculate the delta value, okay, and that will be also calculated through the back propagation, and then adjust it. And then when I iterate through this whole process of feed forward and back propagation over a period of time, what will happen is now these connections and the embeddings will kind of come to an optimal value, because your loss that is arising out of those values, it's a minimum, isn't it? That means if you take that network, that means you would take those embedding values and those connections, then we are getting the most optimal representation and we are getting the minimum loss. So that's the best model that you are getting. So now I could take a very new sentence to classify, and the new sentence contains certain words like this. You simply pick up those embeddings because those embeddings are finalized now, and then input to this particular neuron and a fully connected layer, it automatically predict the value of Y. Okay, so this is what how the new embedding layer is introduced into the system. Okay, and this is what we have also tried as a hands-on exercise in the day 2. Okay. Any more questions on this one? So what we'll do is we will do little embedding exploration today. What are the embeddings that have been generated? So can you go ahead and open this IMDb classification again? Open with Google Colab. Can you open it and then connect? Then execute, you connect your Google Drive. You might have to change this path. Okay, if you remember, you can go to the folder, drive, my drive, and go to your respective folder LLM, wherever you have stored the data, store the files, and you can look at embeddings, right? You can look at the where the file label training data.tsp is there, and you can take the copy path, right? And then you can change this. We've already executed the steps, so you do that, and you can execute until the point that you have done already. For example, model 4, I don't know whether we've gone through model 4. Did we discuss dropout?
Yeah, we did.
Okay. Okay. So until this point, you can say runtime, run before. Run before means run all the steps until that point. It'll probably take 30 seconds to do that, or maybe a minute. And once you're done that, can you say yes on the chat window? or you can simply run that model 4. If that's what you're going to do. No, it doesn't do that. This is not good. It'll take a while. I think about 4 or 5 minutes. Please say yes on the chat window if it's done, executing. Yeah. So while doing so, let me discuss a concept that we'll do is let it execute in the meantime until model 4, right? Then we'll discuss few things. For example, if if embeddings, right, that gets generated out of this learning process, right? So of course, we will have 2 layers here, primarily at a high level. One is called your embedding layer in the network, and the other one is basically called your what? Fully connected layer. Okay, this is very similar to if you have worked on computer vision images. We have a CNN layer with a max pooling and then fully connected layer. And then this embeddings that will be generated, right, for different words, W1, W2, and all that. So what you can do is we can look at these embeddings that have been generated and see and go and verify if the embeddings generated hold the relationship between the words as we expect from the semantics perspective. From the semantics perspective, right? What does that mean? That means if there's a word called good, right? If there's a word called better, right, or awesome, or there's a word called bad, right, or terrible, right, or worse. Of course, there have been different words would be there to express the sentiment of the, and then what you can do is if this embeddings contains or represents the true semantics of these particular words, then you can go and look at the relative position of these words in the this multidimensional space. For example, if you look at the similarity, semantic similarity between good and better and good and terrible, right? So this is basically the concept is called semantic similarity. Okay, semantic similarity, right? So what I can do is you can go and look at what is the vector for good and what is the vector for better and what is the vector for terrible, and then you can calculate the cosine similarity. Okay, so the cosine similarity between good and better, and if you compare with the good and let's say terrible or worse, right? So the cosine similarity should represent what? this similarity should be very, very what? High. Or if I look at Euclidean distance, and the other way around, Euclidean distance. So this distance should be smaller, and this distance should be larger. Or if you look at cosine similarity, this should be, the similarity should be very high here, and similarity should be low here. What about distance, the metrics that we use? Based on that, we can actually go and look at this. Okay, so if we believe that this embeddings generated from this learning process truly represent the semantics, and which in a way intuitively we understand, because ultimately you know the accuracy of the model is quite high compared to simply feeding the model the word exists or does not exist in a sequence. We also represent, the moment we introduce this embedding layer, we saw the accuracy is improved. So in a way, we kind of get a sense that the embeddings might have captured the true semantics of the words, but this is, you can go and actually verify them, okay? And which gives rise to this wonderful idea called semantic similarity, okay? So semantic similarity is actually very important concept today. If you look at all these search engines, all right, whether you talk about Google search or basically enterprise search engines like Elastic, all right, so they have all moved away from something called inverted index search. They moved away from the inverted index search to something called semantic similarity search. Okay, and most of them are actually based on this concept of embedding. Actually, we'll look at that, some of these ideas. In fact, we have an example that we'll do semantic similarity and look at that. Okay. Yeah, somebody I think have a question. Yeah, go ahead.
Yeah, so my question is that, let's say if we calculate the semantic similarity of two words in a corpus. So in one document the word can mean something else, and in the other document the word can mean something else, like it can be context based. So does it also take into account the context, or is it just specific to what the word means?
So, of course, we'll come to some advanced concept later. That basically you're talking about polysemy, right? The word can have multiple meanings based on the context itself.
Yeah.
Right? So yeah, so that is, in this particular example, it's not taken care of. Okay. So when we understand a concept called attention, where it actually captures the contextualized embeddings. Okay. So first understand this, and we'll look at some of the limitations of this particular approach itself. And then we'll go look at how those are taken. I mean, that's a pretty good question, because quite a few words will have those kind of meanings actually based on the context and sentence. So how that is being captured, and that is built on top of this. That's not something very different, right? That's built on this idea. So first we calculate embeddings, then we look at something called attention. We'll come to that.
Okay, thank you.
Okay, and we looked at the accuracy was about 86%. And we can also look at, we can take the model, predict, and predict the Y values. The predict actually gives you the probability values. So the probability is more than 0.5, we can say it's positive sentence. If it is less than 0.5, it's a negative sentence. And then you can build a confusion matrix. I think most of you will be familiar with the confusion matrix. So I'll just quickly go through this. So this is your true positive, right? This is your true positive. Sorry, what happened to this? This quadrant is called what? These are predicted levels. These are true levels, right? So these are the actual ground truth, and this is the columns are predicted levels. So this quadrant is called what?
False positive.
False?
Positive.
This is false
No,
negative.
false negative. False negative.
Yeah. So this is false
True.
positive, and this is true negative.
True negative.
Of course, depends on the context. We can measure different metrics here. But here we'll look at total accuracy only. So total accuracy would be nothing but your true positive plus true negative divided by TP plus FP plus FN plus TN, right? But in specific case, you might have to look at precision recall, but that's fine. And there is a beautiful API there in scikit-learn called classification report, which gives you all the information, right? So normally you look at this particular row, which is basically the precision recall F1 score for the positive classes. Okay, so our F1 score is 0.87, total accuracy is also about 0.87, which is pretty good model. And then what we'll do is we'll look at the peeping into the embeddings. Okay, if you have any questions here, let me know. Otherwise, we'll look at the embeddings. So if you want to look at a specific layer in a neural network, what you can do is when you define this, add this layer, right? You can actually give something called a name. Okay, if you're going to add a name, you can later retrieve those layer information from the network to just have a look at it. So you can say model.get layer embeddings, layer embedding. So this is basically your embedding layer, right? And then you can say get weights for that layer. Okay, and if you look at the dimension of that, it basically says what? 10,000, 8. Can you tell me why it's saying 10,000, 8?
Because there are 10,000
10,000.
words and 8
Eight.
dimensions.
Because we told maximum number of
10,000.
vocabulary size is 10,000, right? We indicate and then 8 dimension, right? So you can see it has generated dimension embeddings for all the 10,000 words, maximum number of tokens, right? It has generated embedding for all the 10,000 words that it has. And then if you want to look at the embeddings for a specific word, what you can do is you can go to that particular index. Okay. And how to get the index? From the vocabulary itself. Remember, when I did a tokenizer, we have a index it can retrieve, and I have written a small function. If you send a word, it first get that index at which point of the vocabulary is there, and then go to this layer and retrieve the embeddings for you. For example, this is the embedding for the word called good. All right. So this is how the word good is represented in terms of numbers. Okay. Of course, it cannot interpret this. We can't make any sense out of it. But these are all latent factors. Right. So this is dimension 1, this is dimension 2, this is dimension 3, and dimension 8, and so on and so forth. Right. Similarly, this is the word for great. Okay. All that we can do is what? We can compare them. Right? We can compare them and see where in those dimensions. Assume that these dimensions are, if you intuitively try to understand, right? If you assume that these dimensions, let's say the words are represented in 2 dimensions only, D1 and D2, right? So if you look at the way the words are represented, probably you will say good, right? Better, excellent. They will be kind of clustered together, whereas a bad, terrible, right, words would be clustered together. Should be, at least semantic. So then makes, okay, that means the words are properly clustered based on the semantics. Of course, this is 8 dimension, so you cannot visualize them. But one thing that you can do also is, if you want to visualize, remember you can do PCA, right? You can do a principal component analysis and reduce to 2 dimension and visualize them. Or there is another algorithm called t-SNE, also you can do. So that's also a way of looking at the words. But what we will do here is we'll simply go and look at the similarity. So good, this is great, this is bad, this is terrible, right? Some words. And then we'll calculate the Euclidean distance. In this case, I'm calculating the Euclidean distance between the word embeddings. Okay. and get distance. So I'm writing a function called get distance, word 1 and word 2. So if I give 2 words, what you're going to do is, for example, let's give the word called good and awesome, right? And then word 1 and word 2 is going to retrieve those dimensions, sorry, indexes from the tokenizer. And then it's going to get the embeddings from them and calculate something called Euclidean distance between them, right? So there's a SciPy function there, and the SciPy library there, in which is something called spatial distance, okay? cdist, where you can specify what distance you want. So Euclidean or Minkowski, Jacquard, cosine similarity, whatever distance based on the data that you can calculate here. And if you look at the good and awesome, the distance is same to 0.27. Okay, whereas good and bad, it's lesser actually. Yeah, sometimes comes like that. Bad and terrible is this, the great and terrible is 0.54. Okay. I mean, barring this one, okay, rest all looks very pretty okay. So good and awesome, the distance between them is 0.27. Whereas the distance between bad and terrible is also looks very smaller, and great and terrible looks a little far away, right? In the distance calculation. Okay, maybe you can little experiment with other words if you have, like let's say awesome. Yeah, also a little far away. So you can see how the words are clustered together. Okay, so similar words have very lesser distance, and the words which are different are very larger than, away from each other. Okay, and this is again we have learned with a very small amount of data. So this dimensions, or maybe you can train with a little higher dimension and all that, these dimensions, these embeddings will come out really, really well. Okay, so can you take 5 minutes, and if you see some words, you can think of some words, or maybe in the example, see if some of the distances make sense or do not make sense. Can you take some more time and little experiment with this? 5 minutes. And you can print this in the chat window if you want. Yeah, I think somebody has a question. Jess?
Yeah, so how spelling mistakes will affect the model if there are?
So in this case, spelling mistakes means if the word is not in the
If
word.
data is not that good and spellings are incorrect and like that, does it affect the model or not?
It definitely
Yes.
definitely affects the model. Okay.
It will consider it as a different word, right? If
That
good,
absolutely.
okay.
Absolutely. Absolutely. So that's why we'll actually come to again one concept called tokenization. We'll look at that. Subword tokenization. It'll take care of that to a certain extent, not really to a great extent, yes. If the spelling is different, absolutely it's going to take it as a different word. But what might happen is even the good word with the correct spelling, the correct spelling and the incorrect spelling, if they are used in the same context, let's say both are, let's say somebody writes movie is awesome, right? Somebody writes, right, the movie is awesome, right? And let me write properly. And somebody, let's say, writes this as awesome or something like that, right? Spell mistake. But both the words and the context of where the sentences are positive, right? Both will still be, of course, treated as two different words, tokens. but they probably will be clustered together in the same dimension. They will have a dimensions or embeddings which are very, very similar.
Similar, right? Okay,
Because they are using the same context.
right.
I think one more question there. Pragya, you have a question?
Yeah, so my question is that if we increase or reduce the dimensions, let's say instead of 8, if we do 10, does it mean that the model accuracy will increase?
So there is no empirical evidence like that. Typically, if you expand the dimension, right, if the complexity of the semantics in a given context is very high, okay, so normally, typically, this is the what you can see is the embedding dimension size, right? So let's say you say 8, 16, 20, 30, and all that, right? I mean, if you look at the performance of the model, if you use a very small dimension, it might happen that it's not able to capture or distinguish the semantics of the words from the perspective of the task that you are at hand, right? The performance probably would not be very high, but if you increase, it might increase. But at a certain point of time, it might, there is not much more to capture in the data, okay? So it might saturate, or probably, in fact, sometimes it might overfit, and probably, the performance model may go down also, right? Understood? Okay.
Yeah,
If you use
got your point.
too low a dimension, it will be too shallow, not able to capture. Too high also probably dilute the semantics of the main. Somewhere in between. Again, what is that dimension? We don't know. You have to experiment. So that's basically job as data scientist, right? When you actually train these models, you do a hyperparameter search, right? And you experiment with many models and all that and do it. But nowadays, of course, the dimensions are quite, people use like 1,000, 400, 500 dimensions. Now, OpenAI uses, I think, 1,400, 2,048 dimensions. Something. Yeah, I think somebody. Abhimanyu? Go ahead.
Yeah, so I just want to ask that in case if our corpus have some documents which have exceptionally a high number of tokens in them, so will they be considered as, I mean, I'm just asking basically the outlier detection here. If that, let's say if we have very few documents which have a very high number of tokens, and when
High number of tokens, large number of tokens.
large number of tokens, sorry, large number of tokens, exceptionally large number of tokens, and very few documents there are. So will they be considered as outliers, or while we're doing padding and truncation, so will that create a sparse matrix for our input layer even after using embedding?
No. The first, before even creating embeddings, right? We have to solve this problem of in fixed input length. Okay. You
Okay.
have to solve this problem of what? Fixed input length. Okay. And then at this point of time itself, if you look at all the documents that we have, right? D1 to D100, let's say, and the length 1 to length 100, right? So at this point itself, you have to kind of take care of this extremely longer sequences, like large number of tokens, isn't it?
Okay.
And yeah, so there only you have to say, okay, because only 2% of the documents or 3% of documents are very long, but 97 to 98% of the documents are pretty much, smaller than that. We did this, right? We did that actually. If you remember, we did this.
Yeah.
Big
Sigma
book.
plus
Yeah.
minus 2 sigma, yeah.
If you look at these sentences are extremely long, okay, but in the corpus they only represent 3 to 4%. Okay, so it took a decision that it can be truncated. Okay.
Okay. Thank you.
Then we gendered the embeddings. Anybody got any other comparison of the words? You can print on the chat window if you want. Any other words? Hmm? Yeah, go ahead.
I just have a small doubt. I just want to know if that works or not. So, if we have a distance between good and bad, and we have distance between bad and terrible, so the distance between good and terrible will be like anywhere equivalent to good and bad plus bad and terrible. Will it work like that?
No, that it may not work. They are
Okay.
not linear relations like that. No.
Okay.
So, how do we interpret this? That what distance is a good? I mean, for the performance of our model, that the learned embedding layer is pretty good for our model to proceed with. Then, how do we interpret this? Which distance is pretty good and which distance is not so good?
No. There is nothing like that.
Okay.
You're saying that there is a particular value, or you're saying particular value, you can say this is bad or good. It's a relative distance. We always look at the relative distance.
Yeah, but sometimes like in this case, like the good and bad is 0.17, and then awesome table is 0.36, and 0.27 and 0.17 they're pretty close as compared to 0.17 and 0.36. So awesome and terrible are opposite as good and bad are. So that's what I was asking.
Yeah, but still we cannot look at absolute value of the distance.
Mhm.
We can only look at the relative distance. Of course, in this, see, when you, of course, our training is only very few samples, like 20,000 samples, right?
Okay.
That's why if we look at today, most of the models are trained on like trillions of tokens, right? So when you increase the corpus size, more and more examples, now these distances will come out very cleanly, right? They'll learn better. So that means the relative distance between these words will automatically optimize. So what will happen is, if you look at your dimension space, let's say I'm just giving an example of D1, D2, and some words of positive sentiment are here and some word of negative sentiment are here, right? You might still find some positive sentiment words are in closer to this cluster and negatives are very closer to this cluster. There'll be some examples, right? The whole idea is it able to distinguish between these words, okay, based on the semantics into separate clusters, but exactly distinct clusters may not be possible, especially when you have a lesser corpus size. But what will observe also, as you increase your corpus size, examples and training, and probably number of dimensions, probably these clusters will start, will be disparate clusters. Their distance will be increase, and they'll become much more compact clusters. Okay, so here the variance is still little larger because of the uh, corpus size and examples, sample set, and the dimensions. Okay, but what exactly is the value, that you cannot say.
So basically, this peeping into embedding layer is for getting a sense that it is distinguishing the semantics.
Because we are only doing a, see, our this classifier is a what? It's a discrimination classifier, right? Isn't it?
Yeah.
This classifier basically is saying, can you discriminate between positive and negative? We don't. And remember, these words are also understood, the semantics, from this particular target task at hand.
Mhm.
So that means if they're discriminating, they're away from each other, then ultimate objective of distinguishing between positive and negative are basically achieved in this case.
Okay.
Again, these embeddings do not have a true semantics of these words. They're only learned from the perspective of what?
The corpus.
Yeah, the corpus and the objective we have. Because we
Okay.
are only doing from the objective of positive and negative sentiment, right?
Okay.
Yeah. So that is actually one of the challenge. That's why that will be actually our topic for the next actually. Is there something called, so what we have learned here, I think that's a very good context setting. You asked the question. is it those dimensions or embeddings are actually true meanings of this word? Maybe not, but they are meaning of this word from the perspective of the task that you are solving, right? Whether it's a positive sentiment or negative sentiment. But besides sentiment, these words can also be used in across many other contexts itself, right? So that's where there is a concept called global embeddings, right? This is concept called global embeddings that was created.
So is this the reason that's why large language model are called large language model, because they are heavily they for that accurate result that they provide, they need to be trained on very large corpus.
Yeah, large corpus and large number of parameters also. Both are large.
Okay.
So there
Even for the multimodals also, right?
yeah, absolutely. I'll come to one theory later, maybe tomorrow. I'll explain that what exactly the large means. Okay.
Okay.
So of course we'll look at that theory tomorrow. But one of the question they ask is rather than generating this dimension, for example, if I take these embeddings and apply these embeddings of the words to a different context, for example, I'm doing a complaint category, right? Categorization or something else. So can I simply transfer this? Probably not, because these are only understood from the perspective of a movie review is positive or negative. The context is very, very specific here, right? The data is also used. Now, if you ask me the kind of words that we use, right? The kind of language we use to review a movie would be very different than the language we use to review a product, or in a very organizational perspective, right? In the context. So you have a software product, and their people, how they use language, that be very different than the language we use in the movie reviews, right? So here what we have done is we have taken only movie reviews context. So the semantics embedded as learned would be very, very applicable to that particular specific context itself. Okay. If you change the domain, probably it won't be appropriate to use it there. To a certain extent maybe, but probably not. So now the question they asked is, okay, I think it's probably one of the most important concept is called, can we generate this something called global embeddings, which can be adapted or widely used across multiple different domains, or maybe fine tune little bit for a specific domain. So can we create something called global embeddings? Okay. So then there's a, for example, for multiple different tasks, not only sentiment analysis, multiple different task classification tasks. But then one of the challenges to get a level data, because remember, we were able to generate this embeddings because we had a level data, isn't it?
Yep.
If it did not have a level data, it's very hard to do that. And if you want like millions of samples, right, so that your embeddings will come out very optimally, which represents the true semantics, you might have to use millions of samples and millions of label data, right, which would probably are labeled for many different tasks. So that's where I think one of the most important concept came is something called self-supervised learning. Okay. So you must have heard about supervised, isn't it? What's the difference between supervised and unsupervised?
Labeled and unlabeled data.
Yeah. For example, regression classification here, typically clustering or dimensional reduction, right? So there's a concept called self-supervised learning. Okay. So it's still a supervised learning, but without generating label data. Can you do this? Okay. Because if you can do this, then there'll be abundance of unlabeled text data that can be made available. For example, if you look at the whole of Wikipedia, right? It's a wonderful text. isn't it? But these are not level data. It does not have any, it's simply text, right? And semantic and syntactic relationship can also be learned, which can be transferred to the downstream tasks. So what they came with this concept, the two different concepts came. Again, it is published by Google only. I think most papers have come from Google. So they came with this concept of continuous bag of words model, right? Continuous bag of words model. And then there is something called skip gram model. Okay. So what are they? Is they basically saying that this is kind of next word prediction problem, right? Next word prediction problem. So what you would just take a sentence, right? You just simply take a sentence saying that, okay, I like this movie, okay, because it has a good storyline, let's say, right? And you don't need to understand even it's a positive or negative sentence, okay? We don't want that level data. We simply have this sentence. Now what I do is, now we convert this. So we take this sentence and convert this into samples. Okay, we generate samples using something called self-supervised learning. Okay, which is automatically can generate samples, level data out of it. For example, we'll say, if I like, right, are the two previous words, what should be my next word? This, right? So this is, you can say WT minus 1, sorry, WT minus 2, WT minus 1, this is WT. Okay, it's a sequence, right? It's a time, not as a time series sequence, but still a sequence. That means if I know the previous word, can I predict the next word? Right? And simply I can say, okay, like and this, right? Then movie, isn't it? So I can, what I can do is I can keep sliding and simply generating samples out of it. And then I can train a model on this, right? By knowing. And the reason, because most in a very, there's a nice, understanding and sentence there, we are known by the company we keep. There's a beautiful proverb there, right? Simply the words are basically known, or the words can be understood, or the meanings can be understood with the words it is surrounded by. Okay, or the words it is in the context it is used. So what I can do is I can still learn the semantics for these words by looking at how they are being, syntactically structured in a sentences. Okay, so they came with this new concept. Of course, they tried with multiple different options, and then of course these two ideas came out very, very cleanly and clearly. One is called continuous bag of word model, and something called skip gram model, right? In which what they do is they look at not only the previous two words, they also look at the next two words and say what is the context word, right? So in our example, I deleted that one. But in the example, I can say I like this movie because. So I can say I like movie because, right? And then the y will be this, right? So this will be my WT minus 2, WT minus 1. This will be W what? This will be W
T plus 1.
T plus 1. And this will be W T plus 2. This is WT, right? So you look at the context word and predict what this word. And the context window can be controlled. The context window size, right? For example, you can look at 4 words or 6 words, whatever. Normally, you don't use more than that. And then try to predict what this word will be. Okay. So if you know what the two previous words, then this. And then what you do is you pass them through an embedding layer, right? Now, this is one approach. And the second one is what? Second one is you give the center word and let it predict the context words, right? You can predict all the 4 words in the context size, either 2 words or 4 words. So both are quite popular, of course. Continuous backward word is, of course, very popular. And then you train a model on top of that. Understood? So what you do here is the language. This is basically the starting point of something called what? They started using this term called language model. Okay. Why it's called language model? Now we are not trying to understand any specific task from the sentences. We are simply trying to understand the language itself. Okay, how it is structured and what semantics it has, right? Irrespective of whether it's a positive, negative, or this category, that category, right? We are not using it for any specific objective. We're simply trying to take sentences from the corpus and trying to understand the structure of it, right? And see if the model can predict that structure, the center word or the context word. So that's where they actually use this term called language. Okay, a language, this is called natural language understanding, NLU, right? So we're simply trying to understand how the language is structured. Okay, so the word is proposed called language model. So when you say in your large language model, this is the initial point of language model. Okay, yeah, sorry, ask.
Yeah, so in skipgram, like let's say here we just had one sample, so the model was able to predict the next few words, but in real life scenario, we'll have multiple samples. So just using one word, how does it understand that what the next words might be?
I'll come to that. That's basically probability structure, right? Okay.
Okay.
So it's possible that there are 10 different or 20 different words are possible in the surroundings, isn't it?
Yeah.
Okay. Not just 4 words, but some words probably will be higher, some words probably will be what? Lower. Okay. So based on that, we will basically calculate that. I'll come to that point anyway. Okay.
Okay.
Yeah. So when I take the surrounding words also, what the center word is, that itself might change, isn't it? So if I say this movie is so I liked. So this movie is good, great, excellent, fantastic. There could be so many possible words that can be replaced, isn't it? Isn't it? Not a single word. But then you calculate and estimate the probability of it. I'll come to that point. So what you do is you take sentences like this, right? Now you can take sentences from the whole of Wikipedia. Now Wikipedia contains probably millions and millions of articles, so, and they are very well structured and very well written. Okay, and probably also factually correct as well most of the times, right? And then we take all these articles and start using something called sliding window running across the text, right? And simply generate this input output, right? Based on whether you're using continuous bag of word model. And then what you do is you create a embedding layer and basically a training network like this, right? That means if you feed these 2 words, I'm just simply explained here using a simple example here. Like if you just use the first 2 words, WT minus 2 and WT minus 1, and you can predict what is the next word is WT. Okay. So, and this is again going to be a stochastic model, right? It's again basically going to be a probabilistic model, right? Probabilistic model, right? Because the model cannot predict what the word is. The model can only predict in the whole corpus that we have now, which contains, let's say, W1 to W10,000 words. Which word is the next possible word? I can predict only the word, the probability values. Understood? Okay. And whatever the probability is basically high, we can say that is the most likely word. Isn't it? Following me? So in a way, it is basically estimating is almost like a prior probability. like your name base. So let's say your dictionary contains W1 to W100, 100 possible words, right? Isn't it? So now you're saying that now I have this word called W7 and W11 as the two previous words. Now I'm going to calculate what is the probability, right? The W1 is the next word. What is the probability that W2 is the next word? What is the probability that W3 is the next word? Right? Similarly, I'm going to calculate what is the probability that W100 is the next word. Right? All probabilities would be estimated, isn't it? And whichever has the maximum probability, so that basically becomes our, right? And then we calculate the loss function based on that. You following me? Got that? Now,
Window size is a hyperparameter or keep increasing automatically?
window size will remain same, but it will start sliding.
It start, but the window size, it's a user input, like we input it in the
Yeah,
like, hyperparameter or something.
yeah, you can specify the window size.
Okay.
Okay. Now, if you look at my input neuron here, input neuron is simply 2 words or 4 words or 6 words, whatever, right? Depending on the window size, like you told. But my output neuron, how many? You can tell me in this case, how many output neurons would be? Hmm? I can't hear actually. No background. So if you use this model, my input neuron is how many? Input neuron, if you look at my input neuron, would be probably, just giving it, all right? Maybe WT minus 2, WT minus 1, WT minus plus 1, and WT plus 2, right? 4 neurons. Then we'll have some hidden layer, maybe. But how many output neurons I want here?
One probability, I mean. That's probability.
How many output neurons? So number of neurons output layer would be equal to the number of words possible in the whole dictionary, isn't it? So all possible words, W1 to let's say W100, right? So this is going to be a purely a multi-word, multi-class classification. So saying that given these are the 4 previous words, what is the next word? Is it W1? Is it W2? Is it W3? Is it W4? W100? Okay, and then it'll basically predict the probability. So this is the 0.001, this is 0.002, this is 0.003, this is 0.001. This is 0.07. Okay, so on and so forth. And the summation of all this probability will equal to, summation of probability will equal to what?
1.
1, right? And this is because it's a multi-class problem. We have to use softmax function. Remember, we discussed that in the second day. Softmax function is my basically activation function, the last layer. To ensure that. And then whichever, let's say it says that W7 is the high probability word, right? And then what you do is we look at the corpus now. Which word is actually the next word? If the W7 itself is the next word, then my loss function will be what? Minimum, because it has rightly predicted. Now imagine W3 is actually the next word, but it predicted a probability of 0.7. Then what will happen? The loss will become very high, right? And then we keep on training until these probability values are, increased for W3 and reduced for W7, right? I'm just giving an example of one single sample, but this is how you actually train across multiple different sample sets, right? Following me? So this is going to be a multi-class problem now. If you look at this, is going to be a multi-class problem. And then we are going to learn the whole network. Is this clear now or any questions? One is basically you are predicting the next word based on the context words. Okay, I'm just taking this example further. This is much easier to explain. This one, what happened this? Yeah. This is still not going to consider polysemy. Okay, semantics, yes. Semantics, absolutely semantics is going to calculate. Okay. Now, one challenge, of course, here is one challenge here is in the real world, of course, there are not only 100 words there, right? There are not only 100 words are there. There could be 100,000 possible words, right? In the real world, the possible number of words could be in a dictionary could be 100,000 or 400,000, right? Probably millions of words. So if your number of neurons, output neurons itself becomes 100,000 neurons, then becomes extremely complex network, and again becomes very, very difficult to solve it. Okay. So then they came to this idea. This was actually used in other contexts also. There's something called negative sampling. Have you heard about negative sampling? Okay. So in the negative sampling, what it is, while they're creating sample set itself, right? Have you used negative sampling in any other context of problems, machine learning problems? We normally use in recommended systems also, negative sampling concept. So what they do is, they convert this is actually a wonderful idea to convert a multi-class problem into a binomial classification problem. Right? So you convert the multi-class problem into binomial classification problem using something called negative sampling. So what you do is, so rather than generating samples like this, given this is the input, this is the output, given this is the input words, I mean previous sequence, this is the next word. So this is actually x1, x2 and y. What we do is, instead we make the y as x3, third variable itself. Okay. So if you imagine like this, if this is the previous word, what is the next word? This is x1 and y. This is the previous word, what is the next word? Of course, I'm taking just one word, previous word, just to simply explain this. We can convert this into something called, this is the previous word and this is the next word. Is this correct? Or this is not correct? Right? So I'll basically create a target variable called 1 or 0. Right? So 1, and we'll take these two words and basically, are they actually sequenced next to each other? This is the previous word, this is correct or not? I'll convert that into a target variable. But if you do this, you will only get ones. So from where you'll get 0? Because you also have to have a 0, right? Not only ones. So what you do is, you also look at the words which do not exist as the next word. Right? First you generate all of them, and then you pick up some words like a not and end. The one of the vocabulary does not exist as the next word, so you'll make it 0. Right? So you look for words which does not come at the next, and then we solve it like a binary classification problem. Okay, binary classification problem. And this is much easier to solve because you will only have a single neuron at the end in output layer, which will predict whether the WT minus 1 and WT are appropriately sequenced or not appropriately sequenced, right? So you can actually use this negative sampling technique to solve this problem. Though this is the main idea behind predicting the next word in the, what happened? Yeah, predict the next word. what we do is typically to solve this problem, and simply we actually use a technique called negative sampling, and then we solve it. So pick randomly vocabulary, randomly from vocabulary, words that do not exist, and also create a zero variable. And based on this concept, okay, see, this is one of the ideas that we use recommender systems in negative sampling. We have actually used in one of the case studies. So what I have done is, given the customer has bought this product P1, what the customer is going to buy next P2, or if the customer has bought P1, P3, P5, and let's say the customer has bought P7 now in the sequence. So this becomes the WT T minus 3, T minus 2, and T minus 1, it becomes T. Right? But the problem is the number of possible products in a company are many, like thousands or 100,000 products. So rather than converting into a multi-class problem, we can actually do a negative sampling and convert, saying that the customer has bought P1, P3, P5. The next product the customer is buying is P7. Is this correct? Or P1, P3, P5, P9, we bring a product that customer has never bought and set to 0, right? So then what you can do is, based on this, you can understand the relationship between the products the customers buying together, like association rules, and predict what the customer is likely to buy next. So this is a very nice concept that people use across many different other domains as well. Okay, so just want to clarify, everybody understood the context of why you're doing this? Okay. Now, based on this concept, now there were 3 global embeddings were created. Global embeddings were created. Okay, that means there are institutions which actually trained models on a very large corpus of data. And one of them is basically called globe embeddings. You might have heard about it probably. Okay, globe is called global vectors for word representation. This is actually created by Stanford. We will actually do a little bit of exploration of this. So can you click, I'll give the link on the chat window, can you open it? So global vector for word representation. Okay. So globe is basically an unsupervised learning algorithm. It's actually self-supervised learning for obtaining word representation for vector representation for words, right? So they created these embeddings from, you can see, they actually use the whole of Wikipedia for 2014 and gigawatts, which basically comprises 6 billion tokens. Now, this is almost impossible to train ourselves because this needs a little computational resource. So 6 billion tokens they used, which contains about 400K. That means 400,000, 4 lakh unique words. Okay, so they have generated embeddings for this 4 lakh unique words, right? And those are represented in 4 possible dimensions. They're giving all possible things actually. One is represented as 50 dimension, other one is 100 dimension, 200 dimension, 300 dimension. So they actually trained 4 different models on this data. One with 50 dimension embedding, one with 100, one with 200, one with 300 dimension. Similarly, they have actually trained multiple different models. One is trained on common crawl. Have you heard about common crawl dataset? This is similar to your internet. So they crawl the whole internet, not exactly the whole, but yeah, very large sample of it. So they actually take data from everywhere. So this contains 42 billion tokens. I think this is smaller size actually. That's it. The actual size is for 840 billion. It's almost close to 1 trillion token. Right? This is almost close to 1 trillion token. And they support about 2.2 million unique words. So this might be also, this is probably also trained on multiple different languages, not only English. And there is one more model which is actually trained only specifically on Twitter data, about 2 billion tokens and 1.2 million vocabulary size. Right? So you can see there were 3 initiatives primarily. One is from Stanford called Global Vectors for Word Representation. One is from Google itself called What to Vec model. So they're also taken Wikipedia, whole Wikipedia dump. And then they've also taken some other data sets actually. And the third one is from Meta, Facebook, which is called Fast Text. So there are 3 different, of course, there are some more also there, but these are the most widely used. Fast Text actually has support for many languages. I think this is one of the first embeddings which comprehensively supported non-English languages. Whereas the Stanford one and the Google one basically primarily focused on initially English language. The fast text supports 157. We'll just see that how many different languages are there. So if you're using any other language than English, I think some Indian languages are supported, about 20 languages are supported that you can use it. Okay. So Globe is one of the first representation of a global embeddings using a very large corpus of data created from a common crawl and Wikipedia also both. So what we'll do is we will go ahead and do a hands-on on this. We'll just directly download those embeddings. This is already trained on the data. And we'll download and look at those embeddings first. Okay. So what you can do is do you see this file also, exploring embeddings in your exploring embeddings? Open Google Colab. Then connect it. And once you connect it, there will be a first sentence called wget, right? We'll download this embedding. This is about almost 1 GB file, 822 MB file. We'll start the download and we'll take a break. We'll take probably 5 to 10 minutes. And then we come back, we will actually explore this. Okay. Just run wget. Or maybe before joining the session, 5 times before you can run it. Otherwise, I think you'll disconnect and it's going to be a problem again. Okay. First of all, are you able to open this notebook? Okay. Yeah, let's take a break, quick break. And okay, no problem. That's fine. Anyway, it'll not take more than 5 minutes. So let me also download it. The problem is if the disconnects now, again, we download it. That's fine. So let's come back at 11, okay? Okay, so take a break. Have you run this step? Is it the file downloaded? Just want to check. Can everyone respond, please? Is it downloaded for everyone? Any questions so far? Okay. So if it's downloaded, then we'll go ahead and do something. So this file is about 840 MB megabytes, right? So we'll go and create a directory called Glove and unzip that. Are you able to do it? Then you can see there's a folder created called Glove, and there are 4 files here now. And as I showed you initially, that Wikipedia, right? This is the one that we're downloading, the first one. They have created 400,000 vocabulary tokens, embeddings for each one of them. Uncased, that means all lowercase. And there are 4 different possible dimensions are there. Okay. And they're given in 4 different files here, if you see. So 50 dimension, 300, 200, 100, right? All 4 dimensions. We'll simply take the 51, just explore. And if you do a head, first few correct, first few words, and first 20 words actually. So you can see that now this is the word. The first word is the word the. Okay, and this is the this is the embedding created for it. Okay, this is the embedding created. So this is actually 50 dimension embedding. Like we created 8 dimension embedding through our deep learning process. So they have created it through the self-supervised learning, the process that we learned, negative sampling, continuous bag of words technique, and they've created this, and there you can see 40 dimensions are there. Sorry, 50 dimensions are there. So you can use any of this, but this is the one that we're going to use. And then what we can do is we'll explore this, how these dimensions are coming out very cleanly. Okay. Compared to the dimensions that we had estimated, by the way. Okay. Please let me know if you're not able to download this. And this contains 400,000 words. So the number of lines in this particular file would be about 400,000. We are only looking at the 20. So what we'll do is we will go and load it in memory. So there is a Gengim library, which is very popular for NLP. It has something called keyed vectors. Keyed vectors means nothing but it's like a dictionary, which will have a which will have a name, and that's basically the key, and the value. The value is nothing but a vector, which is nothing but your embedding itself. Okay, so we will leverage that and load it. It takes some time. Yeah, it gets loaded. Now, if you look at this, is basically get loaded. I don't know, it basically keeps the length or not. Let me check. Yeah. If you look at the length of the keyed vector, it shows 400,000. That means it has got 400,000 keys. 4 lakh words are there in that particular. Okay. Now what I can do is this keyed vector gives some inbuilt functions, right? Inbuilt functions that you can utilize. For example, if you say most similar, right? So pre-trained, you take this particular keyed vector and say most similar and give a word in that, right? Most similar. That means what it'll do is, what is the most similar? In this case, it basically uses the nearest neighbor approach, right? Nearest neighbor approach, which is nothing but it basically looks at the distances. So if you say Bangalore, let's say the Bangalore vector is here on this dimension. This is of course 50 dimension, I'm showing that. So what it'll do is it'll calculate distance between all possible vectors, right? And look at the most similar ones. I think it returns about 10 most similar by default. You can look at them. So nearest words which are there around Bangalore, it's basically going to return that. And if you run this, if you see, you can see it prints the city names, other city names. So Chennai, Hyderabad, Kolkata, Ahmedabad, you can see automatically how these words, as per the semantics, are clubbed together. Okay, and this is possible because this is learned from the Wikipedia, and we assume that most of these words, the locations, so it has actually understood that it's a city and location. Nowhere is specified, right? Simply based on how they are placed in the sentences, it is able to understand the word. And when it's most similar, it gives you the appropriate words here. Similarly, if you say most similar to Dhoni, let's say you're saying Dhoni. Okay. Interestingly, you can see Dravid, Yuvraj, Ganguly, Kumble. So if you know cricket, especially, right, you can see all these people are names simply by the names, the words they're placed together. If you say Google, it's a Yahoo, AOL, Microsoft, right? Very similar things which are HP, same thing. Yeah. Are you also able to get the same result or anything else? Of course, I'll ask you a little experiment with it also. So if you say HP is basically Packard, Compaq, and all that. This is case insensitive. So you have to give in a lower case. Because you read that, no? This is all lowercase, uncased. So you have to give the word in the lowercase only. If you give in uppercase, it will say the word is not found or something. Are you getting that same result? And yeah, if you say Wikipedia, it's a German language, English language dictionary, publish and all that, encyclopedia, blog, periodicals, and all that. Okay. Then there is something called analogy, right? Analogy means the comparison, right? This is almost very similar to what he call it king minus men equal to queen minus woman, right? So A minus B equal to C minus D. Right? So if you want to understand D, then you have to, let's say you want to understand D, so D will be equal to C plus B minus A, right? That be actually the equation. So what we do is, you can use the same, most similar. You can actually add CB and A. So let's say we give it 3 different words here. He'll add CB and find the distance between A and say which is the nearest word. Okay. And if you say, if India, what is this? India and Indian, the distance of Indian. So what is Japan? So the way Indian is to India, what is to the Japanese? So if you run this, it will automatically say Japanese, right? That means it says this is where the distance comes into picture, right? So he's saying, if you say India minus Indian, okay, and then Japan, right? So what should be this value of X? So you can say X equal to, you can say Japan plus India minus, sorry, Japan plus India minus India, right? So A, B, C, and D. So automatically basically says it's Japanese, okay, which is very interesting because there is no other information except simply these words are being used in the Wikipedia in different context. What is India and Delhi? What is to France? It basically, Quran basically says it's Paris, right? We say India to Dhoni, and what is to England? It's a Collingwood. Okay, I'm not sure that's absolutely correct, but yeah, to some context it's correct. Okay, and now you can see the difference between the model that we have built and this model is because our model was built on 2 limitations. One is the sample set. We have a very small sample set. And second one is we have built with only a specific context or task objective, right? And it's a purely a supervised learning technique. But moment we change this, like we take a very large corpus, right? Extremely large, whole of Wikipedia, which is like 6 billion, how many, I don't know, remember how many tokens are there. 6 billion tokens, which is extremely large, right? And we did not use any specific task. We simply used the next word prediction. Okay. And that way self-supervised learning. So we try to understand the language itself rather than understanding the semantics for a specific perspective, how these words are structured, the club together, the used in a sentence, in a paragraph or whatever. And you can see all of a sudden a very nice structure around the language has evolved through the semantics, right? Of course, everything won't be correct, but most things, but this is of course one of the first implementation which surprised the world. Yeah. Okay. So what I'll do is I will ask you to kind of a little experiment with it, and let's take 5-10 minutes here. Can you little experiment with it? And see if you can find something interesting, okay, and print that, or something wrong also present, just let me know. It was possible that something wrong will also be there. It's not necessary it has to be always right, but most times it will be there. Try both similarity, most similar, and analogy both. Okay, yeah, any domain, because it has taken whole of Wikipedia. It can be any domain: sports, music, arts, politics, anything will be fine. So I'll just give you a few minutes here and print those results on the chat window. Yeah, something should come wrong. Yeah, Pragya, you have a question?
Yeah, so these distances that we are getting in the most similar, these are Euclidean distances?
Yeah, by default, yes.
Okay.
I think no, I think these are not declined. These are cosine similarity.
Yeah. Okay.
That's why you see the higher the number, closer it is.
Okay. Got it. So I think maybe for string comparison, cosine similarity is a better matrix that's considered.
Typically, yes.
Okay.
So if it's higher the number, the more similar it is. Okay. You can see there are some things, everything is not correct. Some things are still wrong, isn't it? So I think this in Maharashtra, Mumbai, Goa, it's coming out what? Colombo. That's interesting. Yeah. There's something wrong in that. So there could be a couple of reasons, right? Because either the samples do not have enough information, or Maharashtra, Mumbai. Let's say you try something else. This is absolutely wrong, yeah. If you make it Bombay, I don't know whether the term is in, no, something wrong. Yeah, this doesn't come out clearly. That's interesting finding. What else? Anything else interesting you guys found? I don't know that's correct or not. Woman, sister-in-law, and okay, I'll just give you a couple of minutes, okay? Understand. I know, but that's very cultural specific. May not be there. That's also correct. Not correct. So remember, all these models are probabilistic in nature, right? They're stochastic in nature. There is always some amount of uncertainty, error will be there. Okay. It's not possible that every possible words would be, very well represented. There could be possible that some of the words are not well represented, and some of the relationships also not represented. So like parrot and fly, it basically a noun and a verb. I'm not sure if that relationship is captured properly. It's possible that it's, something is wrong. Now, there's a concept of, yeah, I think we'll get started now. There's a concept of transfer learning, by the way, right? There's a concept of transfer learning in deep learning. So transfer learning is kind of also can be used in the context of incremental learning. Right? It's basically called incremental learning. Now, let me ask this question. If you build an ML model, let's say decision tree or whatever, let's say you build a model from the data D0, right? And you build a model M0. And of course, when you deploy the model, you, over a period of time, when of course you generate new data as well, delta D, right? Now, can you simply do an incremental learning of this model M0 with delta D? Simply take this delta D and you train this model, or incrementally update this model. Is that possible in traditional ML? Have you done this in ML? Yes.
I think if the data is labeled correctly, then it is possible.
No, data is labeled correctly. Assume data is labeled correctly. Is it possible? Like, can you build a decision tree with only no, delta D?
But then that would be very small of a data to train the model.
Yeah. So what you can do is you can train the model delta D, but the information that's learned from the D0 will be completely lost, right? So what I'm asking basically, can you update it, right? You cannot do incremental learning, right, in most of the traditional ML systems, right, models. What you have to do is, if you have a D0 and you build a model M0 and you generate data delta D, right, you have to create a new data set with a D0 and delta D, let's call it D1, and that can be used to train the model M1, right? Of course, we can have a sample weights to kind of give different weights to samples, but the whole idea is typically traditional ML models has to be rebuilt from the scratch, okay, based on the old data and the new data, right? Unless, of course, you're using like a stochastic regression and all that. But this is not true for your deep learning models, right? So deep learning models comes with this wonderful, anything that is built with iterative, right? So deep learning model comes with the concept of incremental learning or transfer learning. Okay, that's why they are very popular. So that means if you have a neural network, right? Right? If you have a neural network and you train the model, right, with a D0, so all your connections, weights are all what? Learned, right? And now if you have a delta D, what you can do is, because when you train D0, you randomly initialize these weights, and through feed forward and back propagation, you adjusted these weights, isn't it? Now, when you have a delta D, we can leverage the weights that has been estimated on the D0, right? You simply use delta D as a batch, okay? And fine tune. This process is basically called fine tuning. So you must have heard this word a lot, right? Fine tuning. So you are now fine tuning the model for the specific batch, right? You simply run this batch and do a feed forward and back propagation, okay? And you update these weights, okay? So your starting point would be the concluding point or the end of the learning process from the D0, M0, and then you can create a model M1, okay? So this fine tuning is basically the concept of transfer learning. That means whatever you learned previously, right, you're simply transferring here, and then you further fine tuning, right, the tasks that you're doing. And this fine tuning can be done in many different ways. One is full fine tuning, okay, full fine tuning, or you can also do something called uh, fine tuning of specific layers, fine tuning of specific layers, right? You basically the concept of freeze and unfreeze there, freeze and unfreeze. That means if you have a so in this case, what you do is you have an embedding layer, especially in the concept of NLP, I'm saying you have an embedding layer, and then you have a fully connected layer, isn't it? The two layers primarily. So in embedding layer, you have the embeddings for different words, right? So you have a different words, W1 to W100, and you have a D1 to D8, let's say. And then you have a fully connected layer here. Then what you can do is, the two things you can do. One is you can do, and when you learn this, and when you train this network, what we do initially? We randomly initialize the embeddings and randomly initialize the connections, isn't it? But if you already have embeddings learned previously from a corpus, like a globe vectors, right? So what you can do is you can bring those embeddings here, right? You can simply bring those embeddings here and then you train only the fully connected layer, right? You only do the fully connected layer. So in this layer, what you do is you only train this weights. You simply take the existing embeddings, whatever. Let's say you get a sentence, you search for what words in the sentence, and those words have what representation in the globe vector. You take them, you concatenate them here, right? And simply do it. So this is actually frozen. And this is, of course, trained. Okay. So this is classic example of transfer learning. So you have transferred the knowledge that you have learned, the learnings from some previous task, which is a very abstract high level task, and you brought in here and then do it here, isn't it? Now, other one is you can bring the embeddings, right? Bring the embeddings, and then let's say you're doing a sentiment analysis, right? One is you can freeze them and only learn the weights, that is fine tuning. Or you can do a full fine tuning. You can bring this embeddings and do it, and you allow it to learn the weights and also adjust this embeddings little bit. Okay. Why need to adjust? Maybe this is a very specific task. Okay. Even we have trained these embeddings before corpus, very generic semantics are there. Okay. And what you can do is you allow for this specific, like a sentiment, positive, negative, you allow them to change. Of course, in this case, what will happen is you might not need as much data or as much number of iterations or epochs to train them. So because initially we were randomly initializing and then optimally coming to a point, but here probably will very soon converge into a minima point. Okay. And those embeddings will be little more context specific. So this is how we bring in little more context to the embeddings from the objective we have that we're trying to solve it here. Right. So that also you can do. So there are two concepts here. If you in the deep learning, one is called transfer learning, right? And you can bring the pre-trained weights. Okay, you can bring the pre-trained weights, and you can further fine-tune it for a specific task. Okay, and this fine-tuning can be full fine-tuning or can be a specific layers. Okay, so it allows you to kind of freeze the layers, which layers should not be. So there is a parameter there, freeze this layer, unfreeze this layer and all that. And then you can, once you build a model, and then you can fit the model, right? That actually you can apply, especially when you're doing a network, right? Got it? Any questions there? Yeah, somebody has a question, I think. No. So you can also learn this embeddings from your own corpus also. So I'll show you here. So what you can do is, let's say I have a very small corpus here. So learning our own word embeddings using the self-supervised technique. Right? So learning our own word embeddings, the same technique of continuous backup model and all that, we can also do that. I have done it where only, like 10 sentences. Of course, this will not give us a great embeddings, but just to show the process of it, but you can actually do it for a very longer text. Okay, so from Gen Z models, what to wake. So I'm actually building a what to wake model. Here you can take reviews, a simple 10 reviews, 1, 2, 3, 4, 5, 6, 7, 8, 9 reviews, I think. Yeah, 10 reviews. And then what you're doing is you have tokenized those, right, by spaces. And here you're building the model. You can see that there are two things that we are specifying. One is a vector size. That's a dimension. How many dimensions you create, and that's a window size also you can specify. This is a window is, right, total window size, like 5 words. So you basically predict the center word given the surrounding 4 words. Okay, that's how it is, the window one. And this will automatically learn the model, what to wake model, which is a self-supervised technique. And you can save the model and look at the weights. So let's run this one. Yeah, this is learns very quickly actually. And you can see there are similar words, but these words won't come very nicely because I've only used 10 sentences. If you use little larger corpus, it will be actually fantastic. Maybe 10,000 and 20,000, it can actually be very nice. So do you want to try with the IMDb data set? Can you try this? Can you take randomly 1,000 samples rather than movie reviews? 1,000 samples from the randomly take 1,000 samples from the IMDb data set and then train this. Is it possible? Can you do it? The same data set we have. Level train data CSV dot TSV.
Yes.
Yeah, just try it. Okay.
Manoranjan, I also have one question. So, whatever pre-built models we are trying to use, similar to the Wikipedia and all, so can we first use those model and try wherever there are exceptions, we use the pre-built model and then try our own things to add into that? I mean, is it something doable?
Exception means absence or what?
So for example, sometimes the model is not giving correct things for some of the words or sentences, like the predicted value is not as expected, or there is no word in that particular dictionary, or sometimes. So can we add into that, or can we use that and then we use our own model onto that?
No, you can use that only. We
Okay.
can fine tune it.
Okay.
You know how to fine tune that?
Yeah.
Let's say particular, I mean, it's a very good question actually. If there's a specific words and a specific word or specific words, right, do not are well represented, you are saying, right?
Yeah.
Not well represented. Okay, then you can fine tune it. But how do you fine tune it? You can't change the model. right? The only way to do is if a specific words are not well represented, what does that mean actually? That means the corpus of data that we presented to the model do not have enough information about what this words,
Yeah.
right? So what we can do is we can create a sample, more sample, collect samples about these words, which contains these words, sentences, right? And give them to fine tune the model.
Okay.
Yeah. The only way you can do is basically create more samples. This is almost like any model, right? Let's say you have model bias. So if you've done machine learning model, let's say there's a gender bias there, right? Then what you do, you basically do when you imbalance,
Normalize that or like add some more samples.
right? You sample it and basically do a well representation, right? The
Yeah.
same thing here.
Okay.
So same word embedding and model, you keep it, but fine tune with more samples, which have probably better examples with those words in those sentences.
Okay.
Yeah. Okay. Yeah. So let's try this. I'll give you some 10-15 minutes here. If you let's try it, otherwise we'll do it together. Simply read that data and assign to movie reviews or whatever and train it. Please let me know if you need any help. Okay. Anyone able to do it?
Yes.
Okay. You got anything? So you printed?
Yes. So when I trained it with 1,000, then I was not getting very good output. But then I trained it with 10,000 rows, and now I'm getting good output.
Yeah, fantastic. Yeah, you want to share your screen? Just show the to others. How did you do it? Just
I
text.
actually did it on my laptop, and I'm connected with a mobile phone.
Okay, no problem. I'll show it.
Yeah.
Yeah. You can try this. So you can attach to the Google Drive. This is what you have done. Simply, you can go to the IMDb, the previous one, right? You can copy this and copy this, right? Read the file because you already done it. It's not something very new we are doing. Okay, fantastic. Somebody has trained on the more entire 25,000. Abhimanu, good. So connect this, read that, and then you can take the whole sample as a reviews. Right, read that, and either you can sample it, like I think some of you have done it, right? Like you, how many samples you have done? Probably have told
10,000.
10,000. Okay, so you can take 10,000 samples. Maybe I think he has done 25,000 samples. Yeah, comes out nicely, right? So and then you basically repeat the whole process here. Except movie reviews, you basically use that variable all reviews. And then you basically, in this case, what you can do is to reduce the dimensions little. Sorry, you can adjust the dimension little, like a 50, and you can also put minimum count because if those one word is specifically there only once in the whole corpus frequency, some minimum count you can put so that to eliminate some of the you don't have to train everything. Reduce the vocabulary size. Also, there is a I think parameter called vocabulary size. Also, you can specify vocab size, and then basically train it. It'll take some time, I guess. Um, uh, and then you can look at the embeddings as such. So I'm going to paste this code in case you want to try it out. I'll give 5 minutes. The chat window. Let me put that into a to import. Okay. Yeah. So once you try this, what I'll do is I will just give a context to embeddings, how the embeddings are being used in other domains. So you get, you need to know actually how important these embeddings are. Abhimanyu, can you try some other words also? We also tried some other words, right? Awful, okay. dialogue, premise. Not bad, huh? Not bad at all, right? Storyline is plot, dialogue, premise. Terrible is horrible, awful, but also comes good also. It's okay, but still you can see getting creative. Tomorrow we'll try transfer learning little on a data set, fine tuning. Oh, sorry, did I send this code to everyone or only one? I pasted the code. Okay, so I pasted the code now to everyone. Lokesh, okay. Everyone's got it. Okay, so I think we'll go that. Yeah, now it's coming. See? Awesome, okay, incredible, flawless. Okay. Horrible, awful, terrible, boring. Okay. What I'll do now is I will explain some more concepts now. Are you all done, or do I need to wait for some time if you're running? Can I continue to the theory? Okay, fantastic. So let's look at why embeddings are important is I'll tell you a couple of examples. Embeddings are everywhere. Now, um, in typical ML model, right? Typical ML model that you do, you always have to take context, right, to understand certain things, the importance of those things. I mean, even it's not beyond NLP, sometimes you take inspiration from other domains. For example, in ML model, right, typically when you build a model, y equal to a function of x1, x2, x3, and let's say xn, right? And these variables will be mix of both numerical and what? Categorical, isn't it? Now, if you typically when you have a categorical variable, what you do? How do you transform them?
One hot encoding.
Hmm?
Yeah, one hot encoding.
Yeah, one encoding, right? That's a typical approach that we take. But a problem with the one encoding is there are, of course, quite a few challenges are there. One is this may also lead to sparse vector, right? Especially when you have categorical variable with many very high cardinality, that is very high number of categories, isn't it? Hmm?
Yep.
Second one is the one-hot encoding does not represent meaning of those categories. They simply represent what? Same thing, present or absent, right? Isn't it? So they're highly orthogonal, isn't it? So for example, there's a city as a categorical variable. Then you have a, let's say, Mumbai, Pune, right? And Bangalore, right? And so on and so forth. Let's say you use this categorical variable in the context of demand prediction or demand forecasting, right? So simply the Mumbai's demand forecasting and Bangalore prediction won't be very different because they're still probably, let's say it's a consumer product or whatever. They'll be very similar and could be little bit of variations based on the population, isn't it? The income level and other factors, right? So they're not completely independent. But when you do a one-hot encoding, what you do is Bangalore, right? We say 0, 1 and 1, 0. Okay, so this creates a very orthogonality in the data. First of all, it can lead to sparse vectors and does not have any relationship between these two, but they're not very different. There are some variations out there, but they're not completely orthogonal to each other. So there is this wonderful paper there. I don't know whether you want to read, you can read it actually. Entity embeddings for categorical variables. So categorical variables are actually, there was this challenge in Kaggle some time back where there was this data set called Rossman. Has anybody seen this data set? Rossman stores. Again, demand prediction, store level demand prediction. This is actually a retail store in Germany, primarily selling drugs, medicine, and right. So they had these variables of cities in that. So what they did is they actually built a embedding layer to represent them. So what they would do, they actually, of course, build a neural network model. So yeah, so they built a neural network model where every variable is, of course, they will have many different variables would be there, right? I think it's written here on it. So let me take that. So it will mix of continuous variable and categorical variable, right? Now imagine categorical variable basically the city. So city 1, city 2, city 3, city n and all that, right? So that will be actually passed through an embedding layer, right? And that embedding layer, and let's say you're saying a particular city 1, then that particular embedding would be picked up and flattened out and then we'll concatenate with the remaining continuous variables. Right? Now the number of dimensions you can choose, right? 8, 14 or whatever. And then feed that to a fully connected layer. Right? And then you basically do your loss calculation like MSC. In this case, it'll be MSC because it's a demand. And then we do a feed forward back propagation. So at the end, what happens is what this city actually represents in terms of real semantics, right? From the perspective of demand, right? That can be captured by the embeddings. What actually this city represent? What this city represent? What this city represent, right? So in terms of embeddings, it can be captured. So rather than saying simply 0 and 1. And when they did this also comes out of the paper. And once the embeddings are generated, right? What they did is to verify whether these embeddings have any true meaning. In that they actually put that into a 2-dimensional plot and plotted it. Right? The cities are plotted in the 2 dimension then, D1 and D2. They might have trained on a higher dimension, plotted it. You can read the papers, very nice. And then when they did that, they're very surprised. Okay, if you see the way the cities are represented, they're actually represented the way they're actually geographically located in Germany. Okay, if you look at Germany map itself, right, saying that the cities which are geographically co-located, they have very similar demand for the products, right? This is a very, very interesting paper actually, and very, significant paper. And so that means the model is able to understand that the cities actually have some amount of characteristic attributes or semantics from the perspective of demand, and the geography is very important in this, especially for this particular retailer. Okay, so this is of course, this model also had a better result compared to OHE representation, one-hot encoding representation, right? So what is happening today also, people are converting their categorical variables into embedding representations. Okay. So I would urge, if you just want to go and read that Rossmann data set little, look at that in Kaggle, and this particular paper, if you can read it, that'd be very nice. That gives the importance, how give you actually some sense about how embeddings are important, right? And if you look at embeddings are not limited to that only. I mean, there are 2 more case studies, important cases like Airbnb. There's a case study there. For example, Airbnb has one big challenge is which user should be shown what listing, right? So if you search for a particular stay based on some characteristic, which listing it should be shown. Now, what you can do is, now if you build a model, right? If you build a model, now all user attributes, I mean, there aren't many user attributes out there that Airbnb captures. The only attributes is basically what were previous searches, right? What interactions you had with the listings, what booking history you had, and all that, right? And similarly, about the listing also, the location, amenities, and all the recommendations, all that, right? Now, if you look at the search queries and interaction with the listings and booking history, right, this will be categorical variable again, because if you have a, let's say, interaction with 100 different listings in the previous past, right, and then it'll create 100 variables now, right? And that's again very significant high dimensional data representation. So what they did is they use all this information to create something called user embedding. All right. So they actually create a user embeddings. Now user embeddings, this is actually what is currently deployed in. There's a and this, you can read this actually from Airbnb engineering. So this is what they have represented. So taken all this data, now they're representing every user in something called embedding space. Right? And every listing is also an embedding space. So now these embeddings comprise all the information, compresses all the information, encapsulates in a way all the information that represents the user's behavior actually, right? The user's behavior, the behavior of the user. And in a very dense representation, that's very important again, right? If you have a very sparse representation, that would of course models typically don't really work well for the sparse representation. And these embeddings are nothing but the user's behavioral information that's captured. And this is the listings information that's captured, right? And then what you can do is you can feed this to a model to estimate propensity or likelihood, right? So now this becomes your variables. Let's say you have done it on a 10 dimension and this is on 10 dimension. So 20 variables should be there. And then you can estimate propensity, right? Or likelihood to book. Okay, this is what they do. Rather than creating a variable with thousands and thousands of variables with just an extremely sparse representation. All right. This is very widely used. And then similar something like Spotify itself, they also create user embeddings based on, again, user's behavior, what tracks he or she has listened to, because you might have listened to hundreds of tracks and you can't use those variables as a categorical variables, right? So that's going to be extremely challenging. And then they also create track embeddings. This is of course created from the audio data, like we have created from NLP data. Each word represents some embeddings. They create the clips of the audio, and then looks at the user behavior and looks at the tracks embeddings, fit to the model, again estimate propensity, right? A likelihood to listen to a new track. Like in Airbnb, they estimate what's the likelihood of you listening to you booking a new listing. Similarly, in Spotify, they also do what's the likelihood that you're going to listen to a new track, right? So you can see embeddings are very, very important. Okay, and one of the foundational element for building new age AI solutions. Okay, whether you talk about text, even images are also embeddings are there, and then audio, then even your typical structured data also, you can actually create those embeddings and store it. Okay, and of course, where do we store it? Nowadays, of course, we'll explore one of these concepts later, probably third day or something called vector store, right? So vector stores are new age databases which primarily are built for storing this dense vector representation of entities going forward, and that can be leveraged to build solutions. Okay. Yeah, somebody had a question. Please go ahead.
So, for the Spotify case, is it about next track recommendation you're saying?
Yeah, next track recommendation.
Okay.
Typical recommendation engine, no? When you go to Amazon, what you're likely to buy next. Customer who bought this also buy this, something like that.
Right, got it. Thank you.
Yeah, Pragya, you had a question. Sorry. What had a question?
No question
So
from my
I
side.
had one question regarding negative sentences. Means if the sentence is saying the movie review is not bad or not good, so how those cases are dealt with?
So that's basically contextual embedding. We'll come back to that tomorrow. Or you can also capture that using something called bigrams.
Okay.
Right, two things you can do. But I think you will come to something called contextual embedding tomorrow, and we'll look at that.
Sure.
Okay. Any other questions? So I'll cover one more simple topic now before we break for today. It's called tokenization. Okay. Now the biggest challenge with NLP today is if you see there are 400,000 words are there, right? And such a random representation. Second one is this vocabulary size increases and you cannot capture all possible vocabularies because the words might have many variations of it, right? So what you do is, then they told, okay, how to actually reduce this large vocabulary size? Is there a mechanism? So this all depends ultimately on the tokenization, right? How do I tokenize it, right? So there are 3 different tokenizations they looked at. This is, of course, over a period of time, people have, come out with different tokenization techniques. One is, of course, the word level tokenization, right? You take a space as a separator and captures word. The benefit of this, of course, you can capture, preserve the word boundaries, okay, and captures word level semantics, isn't it? The cons is basically ambiguity, multiple meaning of some words. For example, in our case, in the glow vector, right, there will be a word called bank, isn't it? Now the bank itself will have a one single embedding. What is that representation? But the word bank can have many different meanings, right? Like it's a bank of a river or a financial institution, isn't it? Same thing, there could be many different examples would be there. I'll show some of them tomorrow. Now, but both has the same embedding representation. Okay, so that could be a challenge. Second, of course, the most important challenge is large vocabulary size. You have to deal with the millions and millions of words. Third one is out of vocabulary words. If the word does not exist, you can't do any special handling. It just simply does not exist. You don't have any embedding for it, right? And a little bit of spelling mistakes also could be a challenge. The other extreme is people propose character level tokenization. Don't tokenize by word, simply take every character like A, B, C, and all that. So if you look at this sentence, L will be 1, E will be 1, apostrophe will be 1, and so on and so forth. This will, of course, be a very small vocabulary size because the number of possible tokens, right, will be very small, maybe 100, 200, or 500. If you even if you consider all possible languages in the world, right, maybe 1,000 or 2,000 something, not more than that. Except I think Chinese, rest all will have very small vocabulary size. Mandarin especially. And then it can handle out of vocabulary words, isn't it? You don't have to be, because simply a character level. But it has no meaning actually. The semantics cannot be captured. The L does not have meaning, E does not have meaning. Only when they come together they have meaning, right? And longer sequences. Too many tokens. If a sentence contains, like now we have if you do a word level, maximum length is 552, but if you take character level, it can lead to like 10,000 characters and so on. So that told, okay, let's take a middle path. So this is what is being followed today. Sub-word tokenization. Okay, you split the word into sub-words. How this will solve? So this will have a reasonable vocabulary size. Like for example, if you say playing, you can say play plus ing. Okay, and ing can be reused anywhere, and ing itself will have an embedding, which probably represent it's in the present tense. Ed will have a past tense, right, and so on and so forth. And play itself has a very unique meaning, right? It can still handle some out of vocabulary words effectively. Okay, for example, there was no word called playful in the initial, but you can still use play plus full, okay, and still create some kind of embedding, mix the embeddings and all that. It has some reduced semantic context compared to the word, but still more quite a fair retained. Okay, will have little longer sequence compared to the word level, but not as longer as character level semantics, right? I may request my additional pre-processing to do that. So subword tokenization is probably today most widely used. There are two techniques people use. One is called VPE. In fact, if you look at all your OpenAI or BAD and all that, they actually use these two techniques mostly. There are very specific little variations of that. This is called byte pair encoding, and this is sentence piece encoding. We look at one of them, but yeah, the whole idea is, the question is here now, then how do we actually split this? Whether I split into 3 different tokens, or 4 different tokens or 2 tokens. How do I know how to split this? I'll split it into play plus full, or I'll split into play y plus FUL, or what? How do I actually even tokenize that? Right? What is the subword? Right? What is the subword? We can feed them, right? Because feeding a subword dictionary and all that from that will be limiting. So we want to learn the subwords from the corpus itself. Okay. So BP byte pair encoding is a algorithm which helps you to identify these subwords and create its own dictionary and vocabulary. Okay, from which we can build the tokens. Okay, so this is what actually being used today. So we look at the byte pair encoding algorithm, and we look at the tokenization example also tomorrow when we come back. Okay. So today we covered quite a few topics now, though mostly around embeddings, but we looked at our own embeddings created, global embeddings, right? Explored that. We looked at continuous backup model, negative sampling, right? How to train embeddings from a large corpus of data using self-supervised learning. Okay. So tomorrow we'll explore further, and I think tomorrow will be all the foundations will be over, and then we'll start exploring the advanced topics from there. Okay. Any questions for today?